Hi, welcome to LT Talks. But before going into the lecture, I would like to say something. From now on, you can download the talk slides from slideshare.net, which you will get in the description box. And for this talk, I will suggest to go back and watch the LT Talks 2 on line coding techniques, which is the minimum prerequisites for this talk to understand. And to get the link of the last talk, I will give the link in the card. Okay, let's talk about unipolar encoding techniques. So here is the outline of this talk. First, we will understand the basics of the encoding techniques and what is a digital signal means, and then we will explore the properties and features of the unipolar encoding. Then we will talk about mainly two variants of unipolar NRZ and RZ itself. Then we will wrap up the entire talk with signal grouping. So what is encoding technique? So that encoding technique means that we have some digital data or analog data or whatever, and we are encoding into some signals. Maybe it's digital signal or analog signal. As in the previous talk, I have said that we are encoding the digital data into digital signals. So it might seem that it is the only encoding technique, but it's not. So we will let's see that we can encode the digital data into digital signals, analog data into digital signals, and the same thing we can do with the digital data and analog data in the analog signal also. So what is a digital signal? These are discrete discontinuous voltage pulses, and each pulses is a signal element, and the binary data which is encoded into the signal element that represented by the digital signal. So what does it mean by discrete and discontinuous voltage pulses? So let's see. For say this is our digital pulse, right? I'm sorry. Okay, sorry for this portion. Okay, so in this thing you can see that this portion, the I select another color. Okay, so for say this is 1, this is 0, this is another 1, and for say this is 0. So this is our for say this level represent the 0th voltage, and this represents this for say V. For say this is a positive, V positive, V positive. So here, whenever we are getting some high value, or say VCC value, or say 5 volt or something, we are representing this thing, and then after on the very next time instant we are getting the low voltage. So then it's represented by this thing. But this entire thing is just represent the switching from the binary 1 state to the 0 state. So that means this is a discrete, and here is the discontinuity lies itself. Okay, let's back to the slide. Sorry. Okay, so now we will talk about the unipolar encoding. Why it's called a unipolar, because it's only uses a single polar. I mean, 2 voltages are used, that is 0 and that is another V. For say in the digital systems we already know that we can deal with the 5 volt or something around that. But for say for this talk we keep it abstract, and then we will talk about some say V. So only 2 voltage levels were used. One is neutral or 0 and another is V. And in unipolar encoding there is the digital signal represented by the space and one that is mark. I mean, we call the 0 as space and 1 as mark. And it seems, I mean, here it's like an on and off and on and off like system. So in this case, that we can see it's behave as a switching function. So we also call it as a on-off keying. Now, as we said that we only use a single polarity of the voltage, the bit rate will be same as the data rate. Okay, this is simple, obviously. but as the growing complexity of the need, I mean, it's obsolete. It's not really in use for current days, but we will read it. Okay. The common variant we have talked about, that's NRZ and and unipolar RZ. Okay. So here we will talk about unipolar NRZ scheme. Here you can see there is a clock pulse and there is the data. I mean, there's a clock pulse lies like this. This is on and off. I mean, if you get the one clock pulse, I mean it will be 1 and then it will goes to off. It will trigger. So there is our data. This is 1, this is 0, this is 1 and 0. So this NRZ which not return to 0, we will understand what does it mean. I mean, what not return to 0 it signifies. So whenever we are sending a detailed data of 1, then the unipolar coding also represented as this one. This is the upper voltage. And whenever we getting a data of 0, then we will represent it as 0. So that means within the clock pulse, whenever the data is 1, it never comes back to 0. It will stays in 1 forever if there is no 0 occurs. So that's why it's called a NRZ scheme. So now we will see some pros and cons of this unipolar NRZ scheme. Obviously, as we saw, that this is simple to implement and it requires a less amount of bandwidth. But there is some drawbacks also of this design, that it has no error handling scheme. As we talked in the last talk, that every design scheme, for every line coding scheme, we need some error handling mechanism to make the transmission more efficient. It's not transparent. Any long string of 0 and 1s can create any noise and it will cause some loss of synchronization. And we know that if there is a loss of synchronization, the entire data can be misinterpreted and the outcome of the entire thing will be get erroneous. So there is some presence of DC level signals in the data, and whatever, because of the presence of the DC, there is some disturbance in the output which might change the resulting output in the receiver end. So here, due to presence of low frequency, we know the line coding scheme deals with the low frequency. It entirely suffers from the signal drift problem. So we will see in the end of the slide what is exactly the signal drift problem is. Well, so now here example I have taken that let's go to the slide and let's check. Yes, here. So now see, here is 1, here is 0, here is 0, here is 1, then here is 1. So here what I have mentioned, that this clock pulse, this clock period is Tc. That is Tc. Well, so here I have represent the time T. So now I can make it a larger. Yeah, fine. That's fine. So let's change the color. Maybe that's fine. Okay. So if this is a unipolar NRZ, and if you want to understand what is the nature of this function itself, for C, if there is any one occur in the system, what happens, for say this variable is T here, this T varies, and if there is any one appears, if there is any one appears, then the entire signal becomes 1 and it's never going to 0th level within the that signal. I mean, if there is no 0 trailing with the 1, it remains as 1. I mean, if there is no, if this number was 1, if this one is 1, it might be like this. Okay, but in this case there is some 0, that's why it came back to 0. So if we represented it mathematically, that means we can talk about that for say some function g of t, which represented by v for the entire this time duration, which is 0 less than equals to t less than equals to this tc for this entire time duration, and this gt will be 0 if the 0 occurs. Well, so hope that is clear. So this is, I have written already that the signal becomes V for this entire time duration of this clock pulse. Yes, not clock pulse, sorry. I mean for this entire data as the binary data, I mean, whenever it's 1. So, and whenever it gets the 0 as an input, and this entire coding remains at 0. Well, so here is the entire thing with the clock pulse. As the clock pulse is like this because a clock pulse have to be triggered. So this is the data, this is our data, and this is a unipolar scheme. So here now we will talk about the unipolar RZ. We also see in the, if we go back in the slide, here is also we seen that in case of unipolar NRZ we got this kind of bit stream, and if we take the same example for the unipolar RZ scheme, you can see that whenever we are getting 1, within the presence of 1, this entire coding scheme is designed like that 1 is represented by this kind of shape. I mean, if we go back to this here, and we can talk about this. I mean, for a 1, 1 is represented by, sorry, not this thing. Yes, 1 is represented by this. Here you can see it. This. Whenever there is 1, sorry for my bad drawing. Okay, whenever you are getting 1, so it remains 1 for the half of the period, and then it comes to 0. And if there is no trailing ones occurs in the data stream, it will remain at 0 for the rest. So whenever I'm getting a next one within this clock period, you can see there is a jump, and this thing again and then again come to 0. So, and you can see if I consider this thing, this entire thing as TC, we can see that the data length is TC. Then in the unipolar RZ scheme, I can successfully say this remains 1 up to TC by 2. For the half of the time period of the data, it remains at 1, then it comes back to 0. Well, so that's why it's called the RZ, which represents the return to 0. So then whenever I'm getting 1, it remains 1 for the half of the signal time period, then it came to the 0 for the rest of the part. So here I have mentioned the same thing, and if I want to write the mathematical expression as I have done before, so if there is 1, if 0 appears, it will be 0 for the entire length of the bit. If there is 1, it will remain half, I mean this is the TC by 2, it will 1 for the half of the time, and then it will be 0. Now here I will pause for a bit, and I would like to ask a question for say, if you think that what will happen if this 1 is remain not up to TC by 2, if I extend this range up to TC by 3 and it remains 0 for the rest of the part, then what the problem we will see, or what will happen with the design scheme. So you can think as a homework task that you will change the entire coding scheme, where if there is any 1 occurs, the function remains 1 for 0 less than equals to t, and then less than equals to tc by 3 or something like that, and rest of the part remains 0, then what the risk or the problem we are going to run. Okay, so hope you can think about it. So now there is again the pros and cons of the unipolar RZ. So as the NRZ and RZ both are of the same class line encoding schemes, they have the same set of or nearly same set of pros and cons. So I am not going to talk about pros more because it's again the same. This is less complicated to implement, and there is some spectral lines in the symbol rate which can be used as a clock. Okay, and the unique backdraw of this scheme that it consumes double bandwidth than the unipolar NRZ. Why? Because we can see that it remains 1 for the half of the half of the time of the bit when appears as 1. So it consumes the double of the bandwidth. Okay. So now we came to the last part of the problem, that is signal grouping. I mean, signal grouping is like we will try to understand just qualitatively. I mean, in the polar signals, I mean, whenever it transmitted over the links, there is a transformer or a capacitor couples with the AC repeaters. Okay, so the DC level is removed, converting into a polar format. So at the very low frequency, what happens, we haven't done the power spectrum density, which is termed as a PSD here. There's a non-zero components in there. So that means the AC coupling, whatever the AC coupling we have talked about here in the capacitor, this AC coupling will result some kind of distortion in the output. Whatever the pulse shape, we will see with some figures, and there's some distortion is observed in the output format. And this AC coupled transmission line exactly behave as a high pass RC filters. In case of RC filters, the resulting distortion in the signal amplitude just decays in the exponential pattern. So this term is called as signal grouping. So we can see this as this thing. I mean, if you go back to here in the writing slate, and we can see that whenever I have told you that it is not transparent and it can't handle the long stream of consecutive ones or zeros, or whenever I get the long consecutive zeros, then what it happens? I mean, this thing becomes of this happens. You can see from this down picture, and whenever there's a consecutive one, it behaves as a just a discharging pattern, and it falls like this thing. So this thing is exactly in the exponential, okay, e to the power something in the negative term. So in the capacitor discharge, you can see that the T by RC format. So there's the same thing happening here also. That's called the signal grouping. So I hope you have understand whatever I have discussed in this slide. So in the next slides, we will see the polar line encoding schemes, where we will talk about polar NRZ and polar RZ, where then we will stretch our lecture in the differential Manchester and Manchester also. So if you have any question, comment down below. Thank you.